a lot. It really works if we do.
All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. So first of all, thank you guys for being flexible today and meeting online. So as I kind of mentioned in my email yesterday, I had to take my father-in-law to the doctor. So everything's okay. It's just I just didn't think I'd be able to make it back on campus just because there's a lot of driving to do, and I had kind of other things I needed to do this afternoon. So thank you guys for agreeing to meet virtually. Okay. So the plan for today is we're going to continue with our lecture notes on unconstrained nonlinear programming. Okay. One announcement that I did want to make, just because we are a little bit behind from where I want to be. I am extending the deadline for homework 5. So homework 5 originally was due this Friday. I'm going to extend that deadline to Monday, just so that you have some extra time to work on the Nelder Meet stuff, because my original plan was to finish all the Nelder Meet stuff by today, and that'll kind of close up all the content for homework 5. But in case we have to talk about it a little bit more on Thursday, I wanted to give you guys a little bit of extra time to finish the homework. So homework 5 is now due on Monday, and that date is 11/13. Okay. So that is pushing it a little bit close to the midterm, and so I will post the solutions to homework 5 basically right after it's due. So basically at Tuesday, 12:01 a.m., the solutions for homework 5 will go up so that you can use it to study for the midterm. Okay. So speaking of the midterm, our midterm exam is going to be next Thursday. And so that is should be the 16th, I believe. Yeah, 11/16. Okay. I don't have the study guide ready just yet, and so I'm going to work on the study guide tomorrow morning, and then post it on Canvas for you guys to see. And I'll send an email to kind of show that to you as well. Okay. Let's talk about the format for the midterm, just because this midterm exam is going to be a little bit interesting. Because for the first, because ever since the first midterm, we've kind of done half and half. And so for the 1D methods, you can kind of solve those problems using hand calculations. But for all the algorithms that we've been covering since then, it's basically just been all code. And so I've been kind of going back and forth about how I want to format this midterm. And so what I don't want is I don't want you guys programming in MATLAB kind of during the exam, just because I think that kind of gets a little bit messy in terms of the logistics and turning on the computers and all that stuff. And so here's what I'm going to do for the exam. Okay, so here's what I'm thinking. And so just like the first midterm exam, I'm planning to have about 40% of the points be from just pure conceptual problems. Okay, so you can expect 4 of those. And so, just like the first midterm, you would answer those questions with just a few short sentences. Okay, so four short answer questions, each of them kind of worth 10% of the points. Okay, 30% of the points. 30% of the points will be on 1D problems, and you will be expected to do these problems by hand. Okay. And so for practice on these types of problems, that's basically all of homework 4. I don't think I've posted solutions for homework 4 too, so I definitely need to do that as well. Okay. And then 30% of the points will be the general nonlinear programming algorithm. So that's homework 5. Okay. And so the way I'm going to format those questions is the following. And so I'm going to write what I call kind of pseudocode on the exam. And so you can kind of expect to see not exactly like a MATLAB script, but kind of the same idea, right? And so there's going to be code on the exam, right? Except I'm going to delete certain lines of code. Okay, so basically what you can kind of expect is that you're going to see code that's basically almost the same as the examples that we're going through in class, except with certain key lines that are going to be removed from the code. Okay. Okay. And so you're going to get the majority of an algorithm. So let's say it's like a Monte Carlo method, right? And so I'm going to put down, basically, I'm going to copy the example from the that we did in the class of the Monte Carlo code onto the exam, kind of, line by line. But I'm going to remove certain key lines of that code. And what your job is going to be is to kind of fill in those lines, and I'm not going to be checking for exact MATLAB syntax. And so, if whatever line that you write gives you a MATLAB error, I'm not going to be checking that. What I'm going to be checking more is that, do you kind of understand the concept of kind of what this line of code is supposed to do, and what that line is supposed to accomplish in kind of the greater scheme of the algorithm. Okay. Okay. And so it's almost like a conceptual problem, you know, in spirit, it kind of is. But I want you guys, you know, what I really want you to get out of this section of the course here is a really good understanding of what the codes are doing on a very kind of detailed level. And so, you know, each line of code, okay? And so homework 5, you're doing that to an extent. And so you're kind of filling in the codes and kind of adapting them to the homework problems, you know, but I really want you guys to really kind of understand, you know, how what purpose each line of code serves and what kind of part that serves and kind of the algorithm has out of the play. Okay. And so it's essentially going to be like a fill in the blanks with the conceptual kind of portion to it. And that'll be about 30% of the points on the exam. And so I think I'm probably going to give you maybe 2 or 3 codes on the exam, and each code is maybe have, you know, like 2 or 3 missing lines of code that you're going to have to fill in. Okay. So that's where I'm leaning. I haven't written the exam yet, so I don't know exactly how it's going to work out, but that's kind of what I'm thinking for now. Okay. Okay. So that's the midterm exam for next Thursday. So again, you know, I'm gonna put out the study guide tomorrow. So I had meant to kind of finish that by today, but you know, things happened and you know I wasn't able to get to it. But I will put out the study guide by tomorrow just to kind of help you study for the exam. Okay. All right. Any questions on homework 5 or just the logistics for midterm exam 2? Okay. All right. And so yeah, so that's the midterm exam. I'll go ahead and put out the solutions for homework 4, and you can expect the solutions for homework 5 to kind of follow shortly after it's due. Okay. Okay. So actually, before I really start today, I have a funny story to tell. So I had a friend of mine kind of mix a medley for me because you know I like I've mentioned kind of many times this semester, you know, I'm having a wedding at the end of the semester. And so we wanted to play some custom music during the wedding ceremony. So one of my friends is really good at this, and he kind of put together the medley for us. But what he also did was he gave us kind of an alternate version of the songs that we wanted to play. And what he did was he ripped the audio from one of my YouTube recorded lectures and kind of played that in the background of the song. And so, you know, it's kind of this very nice kind of a beautiful kind of wedding tune. In the background, you hear me kind of in my, you know, in my voice talking about homework 5 and due dates and stuff like that. So it's yeah. My friend sent it to me this morning, and but I couldn't listen to it because I was at a doctor's office, and my wife just texted me and she's like laughing her ass off at the at what it was. And it's actually she's over there right now, still laughing right now. So yeah, kind of a funny story. Thank you. Yeah. So I'm one of those people where I hate listening to the sound of my recorded voice, and so so by the way, you know, I'm not listening to the recordings or watching the lecture recordings after it's done. And so if you ever find an issue about the lectures, you know, please let me know, because I don't watch it myself because it's very cringe inducing listening to my own recorded voice talking about things like optimization and finite element analysis. So yeah, there's that. Okay, so let's go ahead and pick up where we left off last Thursday. Okay, and so let's go ahead. So we were talking about pattern search. Okay. Okay, so pattern search, you know, this is the 4th algorithm that we're going over in this section. Okay, so far we've gone over Monte Carlo, we've gone over random walk algorithms, we've gone over coordinate search, and now we're on pattern search. Okay, and remember the whole idea about pattern search is to kind of you know, be kind of an improvement over the coordinate search. Okay. Okay. And the whole idea with pattern search is to basically kind of accelerate the process by kind of moving in a direction that's going to point us more towards the optimum. Okay. And so visually it kind of look like this, right? So let's say we have a situation where we have the optimal point in our design space is somewhere over here, right? We're going to assume we have a unimodal function with one optimum. Okay. And so typically with coordinate search, the way coordinate search worked was that we would only change one design variable at a time. And so we're kind of restricted to kind of moving in these coordinate directions, either horizontally or vertically in this 2D plane. Okay. Okay. So something like that, right? This is fine. And so if you keep doing this over and over again, and assuming you have kind of a relatively well-behaved objective function, eventually you're going to reach the optimum, right? So you're going to reach that red dot, right? But the idea with pattern search is that instead of taking these kind of right 90-degree angle kind of turns, why don't we take a more direct path like that? Okay. And so that's kind of the extra step that we're adding on top of coordinate search, is to find out, first of all, what is this pattern direction? Okay. And so we find out that pattern direction based on the lengths of the coordinate steps that we did in the previously. Okay. And second of all, how big of a step do we take in that pattern direction? Okay. So that's kind of the two extra steps that we need to add on top of coordinate search. Okay. So on Thursday, kind of the last thing that we talked about before leaving was kind of step one of this process of finding that pattern direction, right? And so I'll just go ahead and kind of summarize it here for you, okay? And so the way we find the pattern direction is after a sequence of coordinate steps, okay? Okay. And so in particular, we're going to call the pattern direction, we'll call it PI, okay? PI vector is equal to xi minus xi minus n, okay? Okay. For this xi, this is the design vector. After a series of coordinate steps, right? So after we've taken a step in each coordinate direction for each design variable. Okay. And this xi minus n, this is the design variable before we took those coordinate steps. Okay. Okay. So we're very much relying on kind of the vector algebra kind of definition of a pattern direction, right? And so it's just a difference of two points. Okay. So that's relatively straightforward. Okay. And once we look at the code, you'll see that it's pretty simple too. Okay. So finding the pattern direction is actually the easy one. The difficult part is determining how large of a step do we want to take in that direction. Okay. And this kind of leads back into our other discussion that we were talking about last Thursday, which is, how do you determine that step length without taking any derivatives of the objective function? Okay. Because when we did our original coordinate search example, the way that we found the step length was basically to use our classical methods, right? So we took a derivative, with respect to that step length, we set it equal to 0, and we solve for lambda. Okay. That's a luxury that's not always going to be available to us, if we have an objective function that's non-differentiable, right? And so, just like you do in the final project, right? And so if you're planning on using pattern search, coordinate search for your final project, you need a different method for determining that step length. Okay. Okay. And so the way we did it was kind of like this. And so, I need a different numbering scheme. So let's say step A for determining a step length is to start with a default step length, or I should say, let's assume a starting step length. Okay. So let's call that, I'll call it lambda naught. Okay. And then what we're going to do is we're going to evaluate the objective function, in two locations. So we're going to evaluate it in, if we were to take a positive step, and the same thing with a negative step. Okay. Okay. And so we're going to take our objective function, and so a positive step would be xi plus lambda naught times pi, okay, versus f of xi minus lambda naught pi. Okay. So we need to add at least two function evaluations here, because we need to know if it's better to step in the positive direction or the negative direction. Okay. Okay. And so ideally, what's going to happen at this point is when we evaluate these two objective functions, one of these two will lead to an improvement of the objective value. Okay. Okay. And of course, we're kind of assuming that we're working with minimization problems here. And so an improvement of the objective function would be a lower value for that objective value. Okay. If this is true, if one of these does lead to an improvement, then we just take that step with that length. Okay. Okay. Right. And so if one of these leads to improvement, we just take that step, and then we just kind of move on from there. Right. We may have a situation where maybe if we took a longer step, we'd see a bigger improvement. But we're going to hope that we kind of pick that up in the later iterations. Okay. If we don't see an improvement, and so if we get a situation where neither the positive nor the negative step leads to an improvement of the objective function, then more often than not, it's because our step length is too large. Okay. Okay. And so if we see no improvement, we're going to reduce the step length. Okay. And so in other words, we're going to take a smaller step. And so the way that we can do that is we can say lambda, our step length is equal to r times lambda. Okay. Where this r here is our reduction factor. Okay. And in order for this to be a reduction equation, r needs to be something between 0 and 1. Okay. So usually you're going to, the value of r here kind of depends on how aggressive you want to kind of reduce the step length. And so, usually for me, I usually like a good r value of maybe about 0.8. That way you kind of reduce the step length by about 20% each iteration, and then you kind of check again. Okay. So that's a little bit conservative, but so it may lead to kind of an expensive, algorithm, but it works pretty well most of the time. Okay. So this is kind of like a good baseline. Okay. But you can adjust that value of r, based on how aggressive you want your algorithm to be. Okay. And so, if you reduce r even more, so an r of 0.5 would basically have the step length each iteration. So that's going to hopefully save you on some function evaluations, but may cause may cause you to miss some things as well because you're reducing it a little bit too fast. Okay, and so after you reduce the step length, then you're basically just going to return to step B. Okay, so you're going to reduce the step length, check in each direction once again. If you see an improvement, that's great, and then you can leave. If not, then you reduce it again. So this is kind of like an iterative algorithm that you have to kind of keep repeating. Okay. And so steps B and C are kind of repeated over and over again until you get an improvement in the objective function. Okay. All right. And so, you might have a situation where, you keep reducing the step length, and then, no matter how small you make the step length, you see no improvement at all. Okay. And so if lambda, our step length, gets very, very small, and so usually we put a threshold on this. So usually we put kind of a limit of how small we can make it. Okay. And so if lambda is less than some parameter epsilon, okay, where epsilon is going to be some kind of small value. Okay, so for instance, we may set it to be 0.0001. Okay, then at this point, what we basically found out is that no matter how small our step is, we can't find an improvement to the objective function. And so at this point, we say that our solution is converged. And so for our pattern search, and coordinate search by proxy as well, this is our convergence criteria. So once the step length that we find is kind of infinitesimally small, then our solution is converged, and we can kind of exit the algorithm, and just whatever was the best design point at that point, that's going to be our optimal solution. Okay. So this kind of mini algorithm right here. So this is kind of like, like we've been saying, this is kind of an algorithm within an algorithm. This can be applied both to coordinate search and pattern search. And actually, in the example that I'm about to cover, you'll see it applied to both the coordinate step steps and also the pattern search step. Okay. All right. Any questions on this before we look at the example code? Okay. All right. So let's look at the example code. So this is posted online. In fact, you should be able to see this on Canvas right now. Okay, so this is the pattern search code. So this is example 4. Okay, and so in this code, you're going to see kind of two main things. So on the one hand, you're going to see the pattern step, and so you're going to see how we're going to determine the pattern direction and taking a step in that direction. But I think more importantly in this code here, you're going to see how we find the step length without taking function derivatives. And so this is going to help you out with 3B and 3C in the current homework. Okay, because in 3B, I think I have you implement just regular coordinate search, but I have you use a different step finding algorithm, and then 3C is just kind of straight up pattern search. And so you should be able to use this for that. Okay, so let's kind of start from the top of the code here. And so from the top of this code, you see that we set n is equal to 50. Okay, so that's going to be the max number of times we're going to iterate. Pattern search is quite efficient if you're running it well for certain problems. And so if you compare this to other algorithms that we have for like Monte Carlo, this is a lot less. Okay, so this is a lot more efficient than Monte Carlo. Okay, and so just like we normally do in these algorithms, we have to define our starting guess. Okay, and then this is going to be our starting function evaluation. Okay. Oh, I keep forgetting to do this, but each all these examples use the same objective function, and so I can kind of bring that forward here. Right? And so the objective function that we're trying to evaluate is this one right here. So we have it's a two-dimensional objective function. So you have x1 minus x2 plus x1 squared plus 2x1 x2 plus x2 squared. Okay. And then for the pattern search parameters, these are kind of the default values that we're looking at. So we're using a lambda value of 0.5, an R value of 0.5, and an alpha value of 0.5. Okay, so everything is kind of 0.5. Okay, and so you see those parameters here. Okay, so S naught here, this is our initial lambda value. R is the reduction factor, and this alpha value is another step length, but that's for the pattern search step. Okay, so this S0 is for the coordinate search steps, and alpha is for the pattern search step. Okay, from there we launch into the algorithm. Okay, and remember, in order to run pattern search, you have to first take steps in the coordinate directions. Okay, so first thing we're going to take a step in the x1 direction, and so you can see here that I'm modifying x1, and what I'm doing is I'm taking these steps in the positive and negative direction. Okay, so that's what these lines of code are doing here. And so first we're taking a step in the positive direction. So we said that x1 up is equal to x1 base plus s, and then we evaluate the objective function there. X1 down is equal to x1 base minus s, and then we evaluate the objective function there. Okay. And then what this while loop here is going to do is that this while loop is going to continuously check to see if we see any improvement. Okay. And so if you look at the conditional for this while loop, you can see here we have 3 conditions, right? And so if f1 up is greater than f1b, okay, so FB right here, that's the current best value or the objective value at our current point, okay? And we're doing the same thing for F1 down, right? And so as long as these two things are true right here, and so what these two things are checking here is to make sure that, if when we're taking our steps, our steps don't lead to any improvement in the objective function, right? And so if both F1 up and F1 down are greater than FB, that means we're not seeing any improvement in the objective function by taking these steps. Okay. All right, and so remember, if we're not seeing an improvement in the objective function by taking steps, we're going to reduce our step size. Okay, and then the other thing we're checking to see is if our step size is greater than the convergence threshold. Remember, if the step size gets too small, then what we're saying is that the solution has converged at this step. Okay. Okay, and so inside this while loop here, you can see here that we have these 4 lines of code. These 4 lines of code are identical to these lines here, 31 to 34, okay? Because what these 4 lines do is that they take kind of a test step in the positive and negative directions. We're evaluating the objective function in those directions, and we're checking to see if there's any improvement, okay? The only difference inside this while loop is that we have this additional line of code where we're reducing our step size, right? And so we're saying S is equal to R times S. Remember, R is some value here that's less than 1. And so if we multiply something that's less than 1 by S, then that's also going to reduce the step size. Okay? And so inside this while loop, we're basically reducing the step size, checking to see if we see an improvement. If we don't see any improvement, then we kind of return back here, reduce the step size again, check the objective functions, and so on and so forth. Okay. Okay, and then once we're done with that while loop, presumably once we're done with this while loop, either one or two things have happened. Either, we find an improvement, and so we find that either F1 up or F1 down leads to an improvement in the objective function. Okay, and so if that were true, then we're basically going to, take a step in those directions. Okay, so that's what this if statement does. And so what this if statement does here is that it checks to see, which one between F1 up and F1 down does lead to that improvement of the objective function. Okay. And then we take that step in that direction. And so if F1 up is less than F1 down, then we take a step in the up direction. Else, if F1 down is less than F1 up, then we take a step in the negative direction. Okay. So that's kind of one case of if we're exiting this loop. If not, then we've converged. And so, if that were true, then taking a step in either direction is not going to lead to an improvement. Okay. So either one of those things are true. Okay. All right. Any questions on this part of the algorithm here? Okay. All right, and so we're going to basically repeat that exact same code just in the x2 direction. Okay, and so in the x2 direction, we have this code here. So this is basically identical to the code that we have up here, except that we're stepping in the x2 direction. So this is kind of the second step of our coordinate search. Okay, and so the second step we're changing x2 and modifying that. Okay, and so this code's mostly the same. And so, I'm not going to kind of go through it in detail just because it's the same as above. Okay. Okay. And so one other feature that I've added to this code. So these parts are optional here, but just so that you can kind of visualize and see what's going on throughout the algorithm, I basically set the code to print out what the various step lengths are, so that you can kind of see what they're printing out. Okay. Okay. All right, so those are the two coordinate steps, right? And so we need to do those each iteration before we can determine the pattern direction, okay? And so the pattern directions are going to be, in this case, it's going to be two entries because we have a two-dimensional optimization problem, okay? And so we set S1 is equal to x1b minus x1 best, okay? x1 best was the previous best point before we took the coordinate steps. And same thing for S2, right? So S2 is going to be x2b minus x2 best, okay? Okay, and so from here, we're going to start taking steps in that direction. And so we're going to say alpha is equal to alp2 plus that, okay? And so we're going to make the changes to both x1 and x2. And then same thing here. And so we're going to basically keep iterating until, and reducing the step size alpha until we see an improvement of the objective function, okay? All right, and so after we do that, we report the alpha length, and then we take a step, okay? And then if we've converged, then we go ahead and break. If not, then we go ahead and reset our point, and we start back all over again, okay? And then you kind of go through that whole thing. So the most important parts of this algorithm, are this part here, determining the optimal step length, and so make sure you kind of understand this part here, okay? And then the other important part is the pattern step, is where you first of all find out the pattern direction, and then you take the optimal step in that direction. Okay. All right. Any questions on this before we move on to Nelder-Mead optimization? Okay. All right. Let me turn on the light actually, because it's starting to get really dark in here. you. Okay, so let's go ahead and return to the iPad and let's go over our last algorithm in this section, Nelder-Mead. Okay. So all that information should take you up until the end of problem 3 on the homework. So you should have everything for problem 2, A, B, and C, and you should have everything for problem 3 now, A, B, and C as well. Okay. So the last problem on homework 5 has to do with this last algorithm called Nelder-Mead optimization. Okay. Okay. So this is the only one here with kind of a strange name. I guess, well, I guess Monte Carlo was kind of a strange name too. But this algorithm was named after the two dudes who came up with it. So Mr. Nelder and Mr. Mead. Okay. So that's the official name of the algorithm. The official name is Nelder-Mead. But kind of the other name that I like to call it is I call it kind of the other simplex algorithm, or the other simplex method. So we've already seen a simplex algorithm. So we've already seen simplex algorithm for linear programming. This is kind of another simplex algorithm. It's completely different, and so of course this is nonlinear programming. So we're not limited to linear functions anymore. But this kind of uses kind of the concept of simplex just in a kind of a very different way. So it's confusing, and so sometimes you'll see textbooks and the literature call this the simplex algorithm or simplex method. It's different than the one in linear programming, which is very confusing, I know, but optimization people like to use simplexes for whatever reason. Okay. Okay. So that's why, for myself, I mostly call it the Nelder-Mead optimization, just because that's, the Nelder and Mead only came up with one optimization together. Right? So, there's no confusion in terms of what they've done. Okay. And so the whole idea behind the Nelder-Mead optimization is that it uses the geometric concept of a simplex to kind of continuously improve upon your objective function. Okay. And so, of course, the key here is being, this what I've underlined here, which is the geometric concept of a simplex, right? So, like I mentioned before, we've used simplex within the context of linear programming, but we didn't really talk about the geometry of what a simplex actually is. We only talked about simplexes in linear systems. Okay, so let's kind of define what a simplex actually is. Okay? Okay? And so a simplex in geometric terms is a polygon that's formed by connecting n plus one distinct points in n-dimensional space. And so the exact shape of the polygon depends on what dimensional space that you're in. Okay. And so let's look at two examples. And so, the two examples that are easiest to illustrate is just 2D and 3D. Okay. And so in 2D space, okay, 2D space, our n is equal to 2 here. Okay. And so our simplex is going to have n plus 1 or 3 distinct points. Okay. And so if we take kind of 3 points, okay, and we connect them together, so we're going to connect each vertex with each other, right? 1, 2, 3, you can see that geometrically what we have here is a triangle. Okay. The next one that's easy to visualize is 3D. Okay. So in 3D, n is equal to 3. And so our simplex is going to have n plus 1 points. And so n plus 1 is 4. Okay, so we're going to draw 4 points here. Okay. We're going to connect every point to each other. So every point is going to be connected to the other via an edge. Okay. And so kind of remember, we're in 3-dimensional space. And so I think kind of probably the better way to illustrate this is that, this edge here that connects the two kind of side points is kind of behind the, the shape here. Let me kind of draw a dotted line to kind of illustrate that. And so what we have here is a 4-sided pyramid or a tetrahedron. Okay. So simplexes exist for 4-dimensional space, 5-dimensional space, 6-dimensional space, for so on and so forth. It just becomes a lot harder to draw in 4D. But in 4D, just imagine that you need the exact geometric shape that it forms is less important. The more important thing is just how many vertices or how many points that you have. Okay, so whatever kind of n-dimensional space that you have, you need n plus 1 distinct points. Okay. Okay. All right, so that's kind of the idea of a simplex. It's to kind of keep track of each point in n-dimensional space. Okay. All right. And so if we consider the vertices of the simplex as distinct design points in our design space, okay, right? Then what we can also state is that each point represents a particular design or set of design variables. And then each point in the simplex is also going to have a corresponding value of the objective function. And so, I'm gonna draw on the triangle here just because it's kind of easy to see. And so, we have F1, F2, F3, okay? Where F1, F2, F3, those are the values of our objective function at each of those design points. We can do some interesting things with this. And so, based on those values, because they're all distinct design points, they're likely going to have different values of the objective function. We can do things like ranking them in order of, what's the best point to the worst point. And then we can kind of remove the worst point and kind of manipulate. Basically, the idea is to manipulate the shape and size of the simplex iteratively to kind of move it towards the optimal, the optimal point. Okay. And so that's the idea. And so what we're going to do from here, and so what we're going to start today and probably finish up on Thursday, is we're going to talk about what are the different operations that you can do on this simplex to kind of manipulate its size and orientation to kind of move you towards that optimum. We're going to talk about the purpose of each operation and kind of visualize kind of what it looks like in in n-dimensional space. We'll mostly do the visualization in 2D space just because that's the easiest to draw. That's the idea. All right. Any questions on this so far? You can kind of see my cats behind me snuggling on that chair. Okay. All right. So let's go over the operation, or let's go over kind of the algorithm as a whole, and so you can kind of see each of the steps. Okay. Okay. So let's go over what the Nelder-Mead algorithm does. Okay, so first we start with we start with like a step 0. Okay, so step 0 for any algorithm is to determine kind of your initial point. Okay, the Nelder-Mead algorithm is a little bit special because you not only just need one initial point, you actually need a set of initial points. Okay, and so in other words, we need to form not only an initial point, but we need to have an initial simplex. Okay. And so that means, we need to come up with n+1 initial points and evaluate the objective function at each of those points. Okay. Okay. And so, we're going to use the example for 2D. So for a two-dimensional problem, a problem with two design variables, we need to come up with three initial design points. Okay. All right, and so you can come up with these 3 points, or you come up with all these design points in multiple different ways. And so one way is to kind of just pick a center point and then kind of find points all around it. That's totally fine. Or you can use just kind of just kind of do it somewhat randomly, but make sure the points aren't too far from each other. Okay, but you do need that initial simplex. Without that initial simplex, you won't be able to kind of move on. Okay. Okay. So that's step 0. So, kind of before you start, that's kind of what you want. Okay. And so from here, from that initial simplex, we should have, at least n+1 design points and n+1 objective function evaluations. Okay. And so the idea behind the simplex is that once you have the points of your simplex, you'll be able to rank each of the points on your simplex from kind of best objective function value to worst. Okay. All right, so this is really important because we want to be able to essentially what we're going to do is we're going to kind of steadily move the simplex towards that optimum point. Okay, and then based on what you find from this ranking, you can kind of launch into different operations. Okay, so let's go over each of the operations. Okay, all right. So the first operation is known as reflection. Okay. Okay. So reflection is probably the most common operation that's going to be performed in Nelder-Mead out of all the operations that we're going to consider. Okay. Okay. So the idea with reflection is that we are going to pick the worst simplex point. Okay. So the simplex point with the worst objective function value and kick it out. Right. And so we're just like in our linear programming, simplex method. Right. We found the worst design variable, and then we kind of kick it out, right? And so that's going to lead to the biggest improvement of our objective function, or at least that's what we hope so. Okay. 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 So we're going to kick out the worst one, but we can't just kick it out, right? We need to replace it with a new point because we still need to maintain our simplex shape. Okay. So we're going to replace this one with a new simplex point. Okay. And so, of course, the next question is, how do we determine, the coordinates or the values for that new point? Okay, that new point is going to be a reflection of the point that we just kicked out. Okay. Okay. And so the idea is to kind of, from our current simplex, we find out which point has the worst value, and we try to move the simplex as far away from that point as possible. And so by moving furthest away from the worst point, then we're hopefully going to move to where the optimum is, because hopefully the optimum is in the opposite direction of that worst point. Okay. Okay. So let me kind of visualize this in 2Ds that you can kind of see what this looks like. Okay. Okay, so let's say that we have a simplex that looks like the following. Okay. So we have a 3-point simplex, and so this is in 2D. Okay. Okay. All right, and so let's say that we have 3 points here. So we'll call this point 1. So we'll say f1 has, point 1 has a certain value of the objective function f1. Okay. Our second point on the right there is going to have an objective value of f2. Okay. And then our third point at the top here is going to have an objective value of f3. Okay. Okay, so this is let's say this is our initial simplex. So these are the first 3 points that we're sampling in our design space. Okay. All right, so for this example, let's say that f3 is the worst one. Okay, so out of f1, f2, f3, f3 has the greatest value. Okay, so in other words, f3 is greater than f1, f2. Okay, it doesn't really matter between f1, f2 which one's greater. We just need to know that f3 is the worst one. Okay. Okay. So we're going to kick out f3. So, we know for sure that this point here is no longer going to exist, right? So we basically kick it out, okay? And so the new point that we add, and so we'll call that f4, okay? f4 is going to be reflection of where f3 used to be relative to the rest of the simplex, okay? Okay, so this is kind of the easiest to kind of visualize in 2D like this. And so let me go ahead and emphasize this line between f1 and f2, right? So remember, f1, f2 are the 2 points that we're keeping in the simplex, right? Okay, so I'm going to draw a line between those two because those two are the ones we're going to keep, okay? And we're going to keep them in that same position. Okay, next thing I'm going to do is I'm going to draw a dotted line between the point that we just kicked out to this line that connects f1, f2, okay? And this dotted line is going to be kind of the shortest distance in between that point we just kicked out and this line. Okay. Okay, so this dotted line that I drew here is the line from the rejected point or from the kicked out point to kind of the line connecting f1, f2. Okay. Okay. So I'm going to call it the midline because that's essentially what it's going to be. It's going to be the line in between kind of where the old point is and the new point. Okay. If I were to continue that dotted line, and so let's say that we're going to move it past this midline here. Okay. And then what I'm going to do is that this dotted line is going to be the same length of the line that we just drew. Okay. Okay. At the end of this line right here, let's go ahead and make a new point. Okay. So we'll call this F4, right? So that F4 is going to form the last point of our new simplex, right? And so if I connect F4 to F1 and F2, it's going to look like this. Okay. And so the simplex comprised of these bottom 3 points, F1, F2, and F4, okay? This is our new simplex. Okay. And so this new simplex was created basically based on a reflection of our old kicked out point. Okay, so we kicked out F3 and we just reflected it across the midline. and then that's going to give us our new point and our new simplex. Okay. Okay, so that's the idea. And so the idea is that, with this new simplex, this new simplex is closer to where the optimum is than previously. Okay. Okay. So that's kind of a nice kind of geometric interpretation. Unfortunately, you can't program geometry, and so we need to have a mathematical expression for this. Okay. And so thankfully, the mathematical expression is quite simple. Okay. And so XR here, this is going to be the coordinates of the new reflected point. Okay. So that would be the coordinates of F4 in the previous drawing. Okay. The formula for this is going to be 1 plus alpha. I'm going to define alpha in a little bit, times a vector XO. Okay. And so this XO right here, this is the centroid of all simplex points except for the one we just kicked out. Okay. So X naught in the case that we just covered would be kind of the average between F1 and F2 in their coordinates. Okay. And then we're going to subtract alpha times XH vector. Okay, and this XH vector here, this is the coordinates of the previous worst point, the one that we're going to kick out. Okay, so that's a formula that you can use to solve for the reflected point. Okay. All right. Any questions on the concept of simplex reflection? Okay. All right. And so let's go over just because I think the concept of XR and XH I think are pretty straightforward, right? Let's go over how to compute X naught. Okay. Okay. And so I think, geometrically, it's kind of easy to see kind of what X naught represents. It's just whatever points you're not kicking out is just kind of the average of kind of where they all kind of intersect here, right? But of course, you can't program geometric intuition. You have to actually put it into a formula, okay? And so X naught here, the way that we're going to compute it is we're going to take 1 divided by n multiplied by the summation of I is equal to 1 to n in this case, okay, of xi. Okay, basically you're taking all the simplex points that you are not kicking out, and you just take the average of each of those vectors. Okay. Okay. So that's X naught. So that's relatively easy to kind of program in the code. Okay. The other parameter is alpha. Okay. So alpha here is essentially going to be a scaling parameter. So you can almost think of it as kind of like the step size that we just went through in pattern search and coordinate search. And so usually you're going to set alpha to be something close to 1. Okay. So alpha is equal to 1. That's kind of the default. And so that kind of leads to a pretty well balanced, simplex algorithm. Okay. But you can also set it less than 1 and also greater than 1. Okay. Okay, and so if you set alpha less than 1, this is going to basically turn your algorithm a little bit more conservative, and so it's going to make it a little bit more stable, and so it's going to be less likely to kind of do weird stuff, but it's also going to make it slower. Okay. Okay. So having an alpha less than 1 is good if you have an objective function that's kind of a little bit it can kind of get away from you a little bit, and so you end up with kind of an unstable solution. Okay. If you set alpha greater than 1, this is going to set the algorithm to be a little bit more aggressive, and so it's going to kind of move the simplex a lot faster, and so it could lead you to convergence much faster, or the optimal solution much faster, but it can also be a little bit more unstable. Okay. Okay. So those are the parameters, for this. And so generally speaking, unless you have a good reason not to, generally what I like to do is I like to set alpha is equal to 1, and so that works well for most problems. And unless you have a kind of an unstable objective function, or you have one that's converging a little bit too slow, then you can kind of change alpha. But if it's your first time, running Nelder-Meet on a new objective function, I would just set alpha is equal to 1, just to kind of start. Okay. Okay. Any questions on this so far? All right, cool. So we are just about out of time, but I do want to kind of motivate kind of the next couple operations. And so there's two more main operations, I would say, and then kind of like an emergency button that we can push as well to kind of in case things aren't going well. But we'll probably start the next class with the next two operations. So one of them is called expansion, and the other one's called contraction. Okay. Okay. So reflections are generally really good. So generally, if you keep reflecting the points, right? You keep kind of kicking out the worst point and reflecting it. Generally, what's going to happen is that your simplex is going to move, in a direction that's going to be closer and closer to the optimum. Okay. Okay. And so if you keep reflecting the worst point and keep keep doing this, in a lot of cases you're going to get closer and closer to the optimum. Okay, but there are some things that may happen that kind of can kind of throw a wrench in this plan. Okay. Okay. And so maybe a better way to kind of describe these other operations is kind of what you do in case reflection doesn't go well, or maybe reflection. And sometimes reflection works really well. You want to do something else, right? But reflections, the reflection operation is kind of the main draw of the Nelder-Meet of the algorithm. Okay, you can kind of think of these other things as kind of alternatives that you can do in case something's happening. Okay. And so the main thing that the simplex algorithm can kind of get stuck with is that if your simplex gets stuck in like a valley, that we say, or it gets kind of stuck in a local minimum. Okay. Okay, so again, I'm going to kind of illustrate this in 2D. Okay, so let's say that this is our simplex here. So we'll call that F1, F2, F3. Okay, and so just like before, let's say that we're going to kick out F3. And so if we kick out F3, we would lead to kind of a reflected point F4 here. Okay, it could happen that maybe F3 and F4, right, are roughly equal in objective value, right? And so ideally, what you would want is, F4 to be an improvement over F3. But, if F3 is the same as F4, then what you're going to keep doing is you're just kind of keep reflecting kind of back and forth, and the simplex kind of gets stuck. Okay. In this case, you need to do something to kind of break out of that cycle. Okay. And so there's a few ways, there's a few things that you can do. And so on the one hand, you can, instead of kicking out the worst point, you can try kicking out the second worst point, okay, and see if that kind of breaks the cycle. Okay. Sometimes that can work. Sometimes that can be enough to kind of break you out of this valley and to kind of continue on with the rest of the algorithm. Okay. If that doesn't work, you may have to kind of change the shape of the simplex itself. And so you may have to either make the simplex smaller and contract it, or maybe you have to make it bigger and expand it. Okay. Or you may just have to kind of blow the thing up and kind of move the simplex points and kind of shift them around. Okay. The other possibility is that maybe you're at the optimum. Maybe that you've already kind of found where the optimum is, and you can kind of stop there. Okay. Okay, so when we come back on Thursday, we'll talk about those different alternatives and different things that you can do in this case, and then we'll go ahead and look at our last example code for this section. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's it. So that's all we got time for. So thank you guys for coming today, and thank you guys for being flexible and meeting virtually. I will be back on campus on Thursday, so you'll be able to see me then. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your evening, and I will see you on Thursday.